Hello, my name is Evgeny Rebrov. I am a chair of chemical reactor engineering at University of Warwick and Queen's University. Today we will tell you about our project which we received from National Access Point at Tyndall about fabrication of microstructured chips for process intensification in fine chemical industry. Nowadays, fine chemistry is under big pressure from market to reduce production costs, and mainly these costs are associated with a big amount of waste which we are producing. So to reduce the number of waste, we need to follow several approaches. One of them could be make intensified processes in a small-scale reactors, so we can control every elemental step at the catalyst surface. For this purpose, we need to go to microstructured devices, which we will show you later on in our presentation. These devices typically have a size of channels in a micron or millimeter range, which intensifies heat and mass transfer. And by doing so, we can create very identical conditions in the different places of this reactor. This allows us to reduce byproducts production via undesirable side reactions. So if we consider example of a restaurant where you need to treat 1,000 people simultaneously, this creates quite a big challenge because everyone has to get a warm meal at the same time. Looking into our microsystem, we want to do the same, obviously at a micro level, but every catalytic site has to be treated with chemicals at the same rate and in order to get the same catalytic production rate. This would guarantee that we will avoid byproduct formation and make more clear products. So this is a typical example of a microfluidic cell. It has characteristic dimensions of approximately 10 by 10 millimeters and a depth of 500 microns. It can be connected to microfluidic connections, so it's actually a flow cell. And we can insert different amount of magnetic microparticles, which has typical dimensions of, let's say, 200 microns, which can be manipulated, and by this manipulation we enhance mixing. However, the problem with original design was that our particles were circulating near the outer surface of such cell, which created a problem how to treat all catalysts equally. So when we decided to contact National Access Point and Tyndall and to go for more challenging designs. Let me introduce Philip Lisk. He's a PhD student working on the project, and Philip will introduce technical details.
So the major challenge of the project was to be able to manipulate the particles and move them using an alternating magnetic field to get the greatest coverage of the fluid possible inside the reactor. So this is our magnet system, and it consists of 4 electromagnets with 4 specifically designed pole pieces on top. And the pole pieces channel the field into the center. And in the center we place our microfluidic reactor, which has the particles inside. And we produce an oscillating magnetic field throughout from the pole pieces, which drags the particles around the reactor itself. And by using the newly designed reactors from Tyndall, we're able to increase fluid coverage through the particle interaction with the reactor walls inside.
Prior to going to actual designs, we did CFD simulations of our devices, and apparently to estimate mass transfer in the microchannels. So behind me you can see one example of such simulations where you can see that the concentration profile goes from maximum concentration to almost 0 in a microchannel, let's say of diameter less than 1 millimeter, showing that these systems are really very efficient for mass transfer. Once we will finish study on hydrodynamics and mass transfer in a single cell, we will move on towards specially fabricated at Tyndall design, which includes 4 equivalent cells sandwiched on top of each other. So we hope that such a design would allow us to increase production rate and effectively in the future target industrial goal of 1 kilogram per day production of pharmaceuticals. Such pharmaceuticals usually cost roughly €1,000 per kilogram. So once the production rate might be not very big, the added value of these chemicals is relatively high. So this could be an interesting business case which we want to explore in future applications.
As part of the NAP433, we use the advanced silicon etcher here to generate silicon microreactor chambers. So here's the control panel to the silicon advanced etcher. We have a carousel unit that transfers the silicon wafer into the reaction chamber, which is based here, using two gases, SF6 and C4F8. We bulk micromachine the pattern that's required, in this case for NAP433, which was a 300 micron deep silicon reaction chamber into the silicon wafer. Here's an example of a silicon etched wafer from the advanced silicon etcher we saw earlier. Similar to NAP433, we had etched micro chambers etched into the silicon. The next requirement was actually to seal this for fluidic testing. What we do here is we add a glass wafer on top of the machined silicon wafer. They're both aligned in a special tool called a wafer bond aligner, which you can see has both top and bottom optics. The two wafers are aligned with the help of a video screen here, clamped, and then introduced into a silicon wafer bonder to do an anodic bond to permanently seal the glass lid to the silicon.